Good morning, everyone. My name is Sam Malik, and this is the third technical briefing at ICSI. I think what we'll do is we'll wait another minute or two to let the attendees join, turn on their computers, log in, and we'll start in about a minute. All right, I think we'll go ahead and get started. Again, welcome to the third technical briefing of ICSI. I will do a little bit of preliminaries here. The way we're going to do this is not going to be run through Cloud, or it's going to be just done through the Zoom webinar. And so if the attendees have questions, I ask that you put your questions in the Q&A. So the Q&A is a feature you can enable at the bottom of your Zoom screen. And in the Q&A, you can also upvote and downvote questions. You know, we would like to keep these as interactive as possible. So, you know, feel free to post questions throughout the talk. And what I will do is I will read the questions and I'll moderate them at the very end. There's also a chat feature. If folks can also put questions in chat, but I think it will be easier if it's in the Q&A. That will happen in one place. Today's speaker is Sebastian Elbaum. He is a professor of computer science and Anita Jones Fellow at the University of Virginia. His research aims to build dependable systems through domain-specific analysis techniques. You know, the list of awards and contributions to the field is long. I'll just point out that Sebastian used to be the steering committee chair of ICSI from 2015 to 2019. We're excited to have him with us today. He's going to talk to us about program analysis meeting robotics. So it's a very intriguing title. It seems like it's going to be very interesting interdisciplinary work that he's going to talk about. And so with that, Sebastian, you have the floor, or you have the mic.
Thank you, Sam, and thank you, Eugene, for the invitation, and definitely I would like to thank the ICSI organizers for pulling such a virtual event of this magnitude in such a short time. Pretty amazing. So let's see how it works. I think if there's one thing that you should be able to take from this talk, and that I hope that you take from this talk, is that there's a huge opportunity for our community to explore this space at the intersection of program analysis and robotics. So what I'm going to try to do through this talk is to explore this space with you and to try to illustrate some of the challenges that are necessary that we tackle as a community, and also provide some of the solutions that we have undertaken to address those challenges, which are by no means complete, and this is definitely a green area. I consider this a green area for our community. So so that we have a common baseline. So let me just start by saying, just like most of you, I'm a software engineer by training. I work on program analysis. And I think what I try to do is conceptually given some form of specification on the program, I try to mix those together. So that's in general what my work is about. And I think most of your work is about as well. Now the form of specification or program, or whether it's an abstraction of the program changes, but we do this all the time. We do this, you know, as we analyze the program statically, or we try to verify it according to spec. We do this as we do testing, where we're trying to generate inputs from a specification to be able to, you know, exercise the program according to certain criteria and check the outputs. We are doing this as we infer models from the program. So we execute a program, or we analyze it and we try to extract the model from it. We do this with runtime verification, where we actually, you know, we gave up on static analysis or verification or testing, and we're just checking whether the property holds at runtime. So I guess, you know, there's a lot of trade-offs between these techniques. Our community builds around these techniques a lot. And what I just want to argue here is that we have, you know, a rich body of techniques that we have developed over decades that is really, you know, they're really powerful and exciting, but they're handicapped when faced with some of the challenges brought by robotic systems. So now to illustrate the problems, I'm just going to use a lot of videos like these that you know, about 10 years ago, I started to work collaborating closely with my robotics colleagues on systems that interact with the physical world a lot. And this particular one is a drone that is going to find a lake, fly over the lake, collect a sample of water, and bring it back for analysis. And there are a lot of phases of these that are, you know, this was circa 2014, just to give you a time frame of these. Back then, it was really challenging to do this analysis. This drone has close to 10 sensors for localizing to make sure that it doesn't go into the water, but it stops close to the water, that grabs the right samples. There's a lot of interaction with the physical world, not just by flying, but actually interacting with the water. And I'll take the, you know, and hopefully you see how beautiful the system is, and you can imagine how excited I was to get a chance to work on something like this. And to do that, one of the key things is to have a good collaborator that knows a lot about the field, that can teach you a lot about robotics if this is not your field. In my case was Carrick Detweiler on the top right. So in the process of working on this project and others, I learned a lot about the complexity of these systems. And I'll try to illustrate some of them. Now, working with these systems, I also came to the realization that our techniques were limited, and I will illustrate those limitations. And I learned a lot about how much the physical world can be uncertain and noisy, and can break the systems that we build. And, you know, in general, when we think about software, and hopefully I'm not driving you crazy with the video, but when we think about software, we do not think about the physical world that much. In general, we think about, you know, what is the minimum scaffolding that we can provide to, for example, test such systems. Now, just to put people at ease, the system was not damaged in this experiment completely, but we did lose it in a follow-up experiment. So there's some cost associated with faults in this system. I think that's a takeaway here. More general, I get a chance to work with other systems. One that I'm particularly proud of is these systems that you see on the top, the different prototypes of the system until the final one. And here on the left, on the bottom left, you see a video of this research prototype that consists of a drone that has a payload that can drop balls that can ignite a fire. Okay, when manipulated, we put alcohol into a ball, and when they drop, they initiate a flame. And this is really good because it helps firefighters fight fire with fire. Now, these balls are usually dropped from helicopters, and it's really hard to get a helicopter to fly safely in an area like that with that much smoke, that much heat. So we're building drones and payloads to be able to do that. And in the process, I think the most exciting part is how do we go from a research prototype to a product where, you know, it's not just about flying by hand, but it's about automatic flying and flight planning and putting these in the hands of end users that are not us, the researchers. So again, this is the type of systems that I get experience with, just to give you context of the robotic systems that I'm going to be talking about. But don't get me wrong, the stuff that I'm going to talk about and the problems generalize to all kinds of systems, including those that blow our mind, like, you know, the Boston Dynamic parkour, for example, and what those systems can do. So again, the takeaway here is there's a huge space of opportunity here, big challenges, and not a lot of solutions. Now, so in this talk, what I'm going to do is, our team has developed a family of techniques to bridge this gap between the program analysis and the mobile robotics world, and what they can and cannot do. But in this talk, what I want to do is I want to focus on a small subset of them, 4 techniques. And the reason why I picked these 4 is because they're going to let me illustrate those 4 kind of pillars of static program analysis that I described earlier. So I'm going to talk about static analysis, in particular type analysis. I'm going to talk about inferring the model through invariants. I'm going to talk about testing and analysis, and I'm going to talk about verification. So let me start with the first problem that these systems have. And one of them is that these systems operate in the physical world. They interact with the world, but the code and the world are really far apart. The distance between them actually can be quite large. So let me show you one way in which this manifests in code. And this is work that I did with my former student, Jean-Paul Orr, and Jean-Paul is now an assistant professor at North Carolina State University. But with Jean-Paul, what we realize is that there's a lot of code that is missing essential information about the physical world. So a code like this, the one I'm showing here, is, you know, it is a snippet that we extracted and abstracted from a ground robot that it generates a plan with series of waypoints. And as part of plans, it computes the distance between 2 set of coordinates. And one of the things that it does to compute that distance is it applies square root to this formula. And now when you look at this piece of code, maybe some of you realize that there's something odd about it, but it's not completely obvious. And actually this code compiles, this code will run, this code will even pass tests, particularly where the values of X and Y are small. Now, if you look at it, let's suppose that we can put our physical world goggles here. And we're not talking about flows, but we're talking about, look, these X and Y's are in meters. And clearly when you apply a multiplication to meters times meters, you get meter squares. But there's something inherently wrong here, that we cannot add meter squares with meters. So this plus operation, adding meter squares with meters, doesn't make sense in the physical world. It doesn't make sense. So the semantics of the physical world do not match the semantics of the program here. And in part, it's because of this distance between the physical world and the code. So this is one of the problems that you see manifested in different ways in the code, but you know, you can see it with the addition of units, but you can also see it with, you know, with comparison of things. You can also see it when there's assignments of, you know, meters to velocity. That doesn't make sense. Physically, it doesn't make sense. So, and hopefully you can imagine that the code can be much more complex, and the manifestations of those errors could require much more analysis than simply one statement. So the problem is that the distance from code and world is far, and our approach to it was to basically devise a dimensional type system that could be applied for this type of errors, but with one caveat that is really important, is that we provided automated physical annotations of the code. So this is not the first time people have tried to tackle this problem. This problem has led to errors that cause really dramatic failures in large systems. But we took a slightly unique approach on how we actually went about automating this process. So we're not asking developers to annotate the code. We actually infer those types. So just to give you an idea, what we would like to do is we would like to go from this statement here, where absolute new force is computed with these combinations of forces and torques, to let's say, an abstract syntax tree that is annotated with the proper dimension or units associated with those types. Now, let me take a short detour. If you're here because you would like to work on robotics and program analysis, then you need to know about ROS. ROS is a robotic operating system. It's a middleware that offers a lot of capabilities and libraries. It offers tools. It offers basically a tool pipeline from building to deploying to APIs that offer common capabilities like navigation and planning and localization, okay? And it's a de facto standard. There's a lot of systems built around this. The majority these days of systems are built this way, and the ones that are not built this way provide bridges to ROS so that you can actually use them with ROS. Okay, so you'll find systems from ARMs to trains that have been implemented using ROS. Okay, so, and the reason why I introduced ROS, because understanding ROS was the key for us to see how we actually provide this mapping. The idea here is that a lot of these systems use ROS and the classes provided by ROS in the APIs to specify particular type of messages between processes. And those messages have, you know, for example, a message may be the geometric message range, which includes 2 3-dimensional vectors for force and torque. So when someone declares that in code, what we are doing is we're providing a mapping from those ROS libraries to units or dimension types, so that when you declare that something is of type range, we know that it comes with a force and a torque, and we're able to assign the particular units and dimensions to those variables. So this is the first secret sauce. Now, this mapping occurs only once because we only need to map the ROS library once. It takes a lot of work to do that and to do it right. But once we do it, we can apply it to a large extent of systems out there. And every time that the developer would use that type, we can actually assign a dimension and a unit to it. The other approach that we took to do this was to understand that, you know, a lot of code has embedded implicit meaning about the physical types, even though it's not explicit. You know, it may be a float, but the fact that this particular variable here is called linear speed x MPS, meters per second, has a lot of information already. That's a very well-named variable, and it provides hints about its type. That variable in this case is of type velocity. We're also using the concept of belief propagation. So in this case, the belief is that if you subtract linear speed x meters per second from vref x is likely to be a velocity as well. We're not certain, but we believe it might. And the idea here, and this is work that we are still evolving, is the idea that you can actually accumulate these beliefs into a probabilistic network and have more confidence about the variable types based on how it is named, how the data propagates, and even how, you know, what type of ROS variable it uses. And this is work with Dr. Zhang from Purdue University and his students. So this is the second way that we provide automatic annotations. And once we have those annotations, we have basically a type system that says unit type 1 and unit type 2 can be added if the type is the same. And when I say type now, I mean physical type. So are they both velocities? Are they both distances? Are they both temperatures? Are they both voltages? And we do the same for comparison, assignment, and so forth. Now, if you're able to annotate the code automatically like that, and you have the dimensional semantics implemented with a type system, then in this example, we can walk the tree and easily detect that this particular addition is operating between 2 different types, and that's illegal. So we found our inconsistency between physical world inconsistency. So do these inconsistencies really happen? It turns out they happen quite a bit. We studied at the beginning 50, 100, I think we're over 200 systems that we have studied. We have a reasonable rate of false or true positives, I guess, over 80%. And I think almost every project that we have analyzed has some type of inconsistency, dimensional, unit, frame, you know, some type of inconsistency as we have studied. That said, we are only able to automatically annotate probably 3/4 of all the physical variables in the code. There are many that are physical that it is hard to do automatically, but this is work in progress. And it turns out that these inconsistencies do matter. They cause failures. They have been fixed when reported, or they have been fixed even before we detected them. And the feedback that we have received from developers is that they really like it. And I think my sense is that they really like it because there's a low cost in terms of annotations, which seems to be key, because annotation of these physical variables, as we have found, is very, very expensive. It's very hard to do well. These units can get really complex, and people can make easy mistakes on them. So I'll stop here with this, but we have a few papers on this area, all come with artifacts and tools, and I encourage you to check them out. Now, so the findings so far is that the distance between code and world was big, but code with dimensional types is a little bit, it's smaller. So we're kind of, tying that distance and making it a bit smaller to this type system. But one of the things that I realized, and this is collaborating with my colleague, Kevin Sullivan, is that this is just one instance of a much larger problem. And the problem here is that, the code is decoupled from physical meaning for these systems when it shouldn't be. So we only have addressed the dimension problem. And with Kevin, we're working on the units problem. So it's not just velocity versus meters, but millimeters versus decimeters versus meters being a problem. And more generally, Kevin and I have been working with, generalization to the laws of physics. Are the rotation metrics that we are applying, do those things have the right properties to being combined and applied to other items in the code? So really, it gets much more interesting and much more complex as we're digging deeper and getting a little bit closer to the world. And the idea here is that we would like to be able to provide a physical interpretation of the code of code that is meant to interact with the physical world. That's where we're going. Okay, so I have provided problem, solution, outcome, and what is coming next, and I'll follow the same pattern with the other techniques. The second family of techniques that I want to talk to you about are inferring invariants. And I think, our community has a history of doing this for programs. And what is unique about trying to infer invariants in this domain is that, well, two things are really interesting. One is the system state is much richer than the code state, because the system state involves more than the code. And the other interesting piece is that the physical state is really an estimation of the real physical state. Your sensors, your code can only estimate what is the physical state of the world. It only perceives a small part of it, and that whatever it perceives is noisy and limited. So that is a challenge. And I'll illustrate again this with an example. So let's suppose that that we want to build a system that will land this drone on this moving platform. And the challenge here is, we can try to land, and if it doesn't, if the conditions are not right, we want to reinitiate the landing sequence, okay? And you can imagine that we think about, okay, well, the drone needs to be close enough to the platform in terms of height and X and Y axis. Maybe their velocity vectors need to be aligned. Maybe there's some acceleration that we need to consider, minimal or maximum acceleration ranges that we need to consider. But it's hard to anticipate all the conditions under which we can guarantee that this landing will be right. So we thought, hey, this is a good idea to think about. Can we generate invariants from common scenarios that we have trained the system for? And if those common, behavior envelope is not respected, we don't want to land. We want to reinitiate the landing sequence. So this is the video that shows this system operating as we designed it and successfully landing on that platform. This is to give you a flavor of how the system operates. A little bit more, you see a little bit of jerking there, but overall, it seems like as long as the velocity vectors are aligned, we can land successfully on that platform. Now, as soon as we introduce some external elements, this is not going to be the case. So on the left side there, you see a fan, and as we try to land on the platform, the fan causes the drone to take a different angle and brake. In this case, the platform was flimsy, and it would have been pretty hard for us to estimate extreme conditions like that. So the idea here is very similar to DICON, is that can we infer invariants for these systems, but they have to include the physical elements. So we want to be able to monitor the system when doing that. And the way that we monitor, going back again to Ross, is we're not looking for pre and post conditions at the function level. Those are too close to the code. What we're looking at are messages between processes in this system. This system has probably close to 10 processes running concurrently, and the information that is passed between them, because that information tends to be of physical flavor. So for example, we can see the pose of the vehicle being passed, or the control state of the vehicle, the command control state being passed, or the UAV pose being passed. So all of these are physical entities that are being passed between the processes in the code in ROS, and we want to be able to capture those, and ROS offers capabilities to capture those at a high level. So it's not about program points anymore. That's the first takeaway. The second issue here is that we are observing these, we're collecting traces, and we're going to be generating invariants like the ones that you see on the left. And some of these invariants are going to be, things that you are used to seeing, from tools like DICON or any other of the invariant tools that we're used to. What is perhaps unique about it is that, so you will have all the variables that you see are of physical nature: translation, rotation, states. But the other piece that I wanted to point out is that you see variables like rate. Now, the rate was not a variable that was part of the code, but it's a variable that we derive as a part of the trace generation process, by realizing that a lot of the variables here make sense, or a lot of physical variables, it makes sense to study not just the variable, but the derivative of the variable, or the second derivative of the variable. So it's not just about the pose, the position of the drone in space, but how quickly the move is moving through that position. Even if that variable is not being reported, we want to be able to generate that, or the acceleration, or anything like that, because those actually provide information about what is the physical state of the drone. In this case, velocity, acceleration, pose, but also the space in which it moves is captured through these invariants. One more thing I'll point out is that we're also capturing invariants of temporal type, like certain events need to happen after others. In our case, motors can be turned off only after you landed on the platform, not before. So the interesting thing about this is that with this approach, and here you see some labels with and without monitors. By that I mean we put those invariants into the code to monitor those invariants, and when they were violated, we avoided landing. So in this case, it avoided landing close to the fan, and it landed when it was far away from the fan. In this case, if we don't have a monitor with the invariants, the drone will crash. However, if we have the monitor with the invariants, it detects that the invariant is violated and reinitiates the landing sequence. And it may do this multiple times until it succeeds or it runs out of tryout times. So this allows us to be more successful in more settings. Now, clearly, this is a very limited context, but the point is to illustrate that we can have these richer invariants that consider the physical space as part of the encoding of those invariants. Now, let me show you a different context, a little bit different, and this is with my student AJ, and again, my colleague Carrick, and this is a problem of trying to transfer a payload between two drones, physical payload. Like, I'm going to pass you a bar with a sensor from drone A to drone B. And we have, this system has 4 stages where you estimate the pose of the drone, you stabilize your flight, you approach it, you grab the bar, and then you release it and go. Now, the estimation is a noisy process. Hovering is noisy. It's hard to actually stay at the same altitude. There are small variations all the time. So actually doing this, grabbing something and running away with it from another drone is actually a fairly challenging project. And there are failures that are not due just to hardware. There are some, I'm going to show you here one where the bar is grabbed, but it slips away. And I'm going to just let it run a few more seconds just to show off AJ's work, because I think we got to the point that we're able to, to grab a bar and hold it from a drone hovering mode. Okay, and that's it. And I'll show you a different angle. But hopefully in the back of your head, you're thinking the invariants that are needed here are really, really harder to characterize than the ones that I showed you before, right? And that's a success one. And we are able to infer invariants like this. We're able to infer that the release always happens after the approach. We're able to understand that release duration is always less than 2 seconds. We're able to generate these invariants, but I think what we realize, and this is when my student Marielle, is that there are many invariants that are hidden from us simply because these invariants are state conditioned. That means these invariants only hold for a particular state of the system, and understanding those states and capturing those states and capturing or generating the associated invariants is extremely hard, because it requires for us to encode those complex states. The other thing that Marielle and I realize also is that we need to deal with noise. These systems are just, it's not like every time that you're in the stage of release, the magnetic sensor threshold will be greater than, the magnetic sensor will be greater than the threshold for 2 seconds. It only happens 90% of the time, 95% of the time. So we need to be able to report such occurrences, because these systems are full of stochasticity that we need to deal with. So the bottom line is, how we are trying to do this is to encode the problem as a Bayesian problem, where we have prior data, we have likelihood, and we use the Bayesian rule to use this likelihood and previous data to estimate what is the likelihood that magnetic sensor threshold is going to be greater. The magnetic sensor will be greater than the detection threshold for 2 seconds, given that we're in the stage of release. Not that this is a conditional probability, not a joint probability. So we need to be able to reuse this. And the idea is that all the traces can be used to refine this information. And the more data we collect, we're going to be converging towards this. But the previous information can be used to inform the future one. Slightly shifting the domain, we're working with Lu Feng, my colleague Lu Feng at UVA, and we're learning how to apply this approach to other systems, like a self-driving car that uses with minimal oversight from the user. And we're learning invariants such as the following, the one at the top there that says, look, the probability for the breaker to be engaged, given that you're in autonomous mode and the pedestrian is on the way, is greater than 96%. So why is 96% not 100? Well, it may depend on other factors that are not captured here. But the interesting thing is that we can see when a break is being engaged and under the one settings that holds. So hopefully from this second type of techniques, what you got is that we need to be able to capture these more complex invariants. It involves handling uncertainty, handles the complexity of a physical state, and that's kind of where we're going with it. Let me shift to the third problem, and I want to talk about testing and analysis and how do we generate tests for these systems. And I think the critical problem here is that the code is subject, when you're trying to test the systems end to end, what you'll find is that the systems are subject to physical constraints. And I'm not going to discuss the other side, but the physical side is also subject to code constraints. So there is this synergy of constraints that operates all the time and that we can use to our benefit in many cases. So typically when you would test these systems, you will think about, components like localization, navigation, controller planning. All these are essential components of all these mobile robots. So when you think about, do I know where I am? Do I know where I'm going? Do I know how to get there? Do I know what commands to exercise on my vehicle so that it will take me there? All of that is an essential part of these mobile systems. And one of the things that we find is that these components tend to be tested under nominal conditions. In the case of the drone, it would be this drone that you see at the top that is going straight on the hallway, and at the bottom you see kind of the same shot from above. That would be a typical trajectory for this drone where I would test it. And when working with our colleague Nicola Beso, he's from systems. What we discover is that what we're interested in is how do we generate tests that will push the system to the limit? And to us, that reminds us to load testing. How do we actually force the system to take those deep cuts that may lead to a collision against the wall? So when trying to test these complex systems, we realized that we didn't have a way to do that. So it was a great opportunity. The problem, though, is that the space of trajectories that you can generate is ginormous. So actually, and the other difficulty is that the code cannot tell what is feasible by the physical drone, what trajectories are feasible, which ones are not, and which ones would cause more stress. It just doesn't have the knowledge of what is the physical structure of the drone and what would those things mean. So our solution to this problem was actually by understanding that we as coders have understanding of the code, the system and mechanical people have a good, clear understanding of the physics, the dynamics, the kinematics of the robot, and we're thinking about how to bring those together. So the key idea here, the key problem is, how do we go from the many potential trajectories between A and B with a lot of waypoints on the way there to something where we prune the trajectories that is not feasible because the drone cannot reach those waypoints in a given time frame. And after we're pruning the trajectories that are just unfeasible physically, how do we identify the ones that cause the most stress? And maybe the ones that cause the most stress are the ones that imply greater changes in velocity. And as we are going to see, is that this is not intuitive, because it depends not just on the physics of the drone, but it also depends on the code and how it controls those features. So my student Carl and I, what we did is, when working with our systems colleague, is realize that there's tons of work, obviously, on kinematics and dynamics and how to characterize the systems. And you can take your pick from a menu of models that characterize how a drone behaves. You can go all the way and pick a model that includes 14, 15, 16 terms on how to model everything from the engine, from one of the rotors in the drone, to the drag, to everything. Now, just to give an idea, this is a kinematic model that includes these 4 sets of equations here, and it takes an input, the rotation velocity of each motor. It translates those into basically thrust, roll, pitch, and as you go on in the equations, you go from these equations over here, which takes these velocities of the rotors, into U1 to U4, which you talk about the thrust, the difference in thrust on the X and Y's and so forth, multiplied by the attributes of the drone, the inertia matrices and things like that. You then use those to compute the angular velocities, and then you compute those, use those to compute the accelerations. So all this derivation is just one part of what a physical model could be. And you can pick a simplified version of them, but the point is that these models can be really complex and rich, and they define how the system can move in space, given just the capability of the hardware. Now, the interesting part is that capability can tell you, for example, what is the reachability set, the physical reachability set. It is not reachability set in the program analysis end, but in the physical reachability set of this drone. So this robot, which is in blue, it tells you that in n units of time, it can reach all this pink area and nothing else. It cannot go beyond that. It doesn't matter what your code says. It cannot go beyond that because it doesn't have the capability in its motors to reach further than that. So as you can tell, if you know that reachability set, we can use it to make these pruning from many potential trajectories to just the feasible ones. And this is kind of one of the secret sauces of Carl's work. Now, without getting too much into the weeds, in order to do this type of exploration, you need to understand ROS, and you need to be able to build stacks of software over it too. control the drone, to simulate it, and so forth. Some of that is offered by ROS, but some of that required for us to build a significant software stack that went beyond the standard simulation that offers, for example, Gazebo or something like that. Now, this graph, what it shows is that the approach that doesn't consider the KD, the kinematics and dynamics of the system, the models that I showed before, we cannot generate many trajectories that are long and still valid. So we'll put waypoints everywhere, but if you go if you want to make a really sophisticated trajectory with many waypoints, the only way to do that is to use a kinematic model. Otherwise, you spend a lot of time generating trajectories that are trash, basically, that the system won't be able to explore. And once you would generate the feasible trajectories, we can execute them. We can learn what stress is, whatever stress measure you pick, and generate, again, feasible trajectories that use that model to guide the generation. So we use the physical model to prune trajectories that are invalid, and we use the physical model also to help us to model stress. And in our case, stress was the distances, for example, between a target trajectory and the trajectory that the drone actually took. So in this example, we see in red that between these two waypoints that our trajectory that we meant to explore, the robot actually compensated, came down and came on this way and that way. So you can see the difference between this green line and the red line was actually significant, over 10 meters. So the drone overshoot that particular piece of the trajectory. And this can be only generated if you have the right sequence of waypoints in space that will cause the drone to overshoot. And let me emphasize this. This doesn't depend just on the physical abilities of the drone. It also depends on what the software can do, given what controllers implemented. Some controllers may lead for you to overshoot a waypoint, but other controllers may lead to a very smooth navigation of a given waypoint. So the combination of waypoints depends on the software controller as well. And that's why there's this synergy between the physical and the code in this case. So the outcome is that we have this really neat approach that will appear in ISTA this year to generate these complementary scalable approaches to explore the physical space of trajectories with robots. And I think where we're going with it, and what I think is we're really excited about, is that in the process we have built simulators and we have built the ability to run these tests in simulation and in the real world in our lab, and we're able to compare them and actually build on each other. So I think there's a lot of space by combining the simulation and real world testing that we're about to explore. So that's where we're going next. Let me just talk about one more problem, and that is the problem that everyone is fairly excited about, which is DNNs or learning components, and how do we go about testing or verifying them. And I think these components are just crucial to these robotic systems. I think you will be hard pressed to find a state-of-the-art system that doesn't have at least some layer of machine learning to process sensor data, to integrate the sensor data at the perception layer or at the control layer. DNNs are going to be at least part of the conversation. And I think the problem that we are facing is that we are trying to provide guarantees through verification that the DNN abides to a property, but the training sets that we have are just such a little piece from the world that these DNNs are likely to, generate functions that cover a lot of ground for which they were not trained. So let me contextualize this into this problem with this particular system. This particular system was not developed by us. It was developed by Loquercier, and it's basically, and his team, and it's about equipping a drone with a DNN so that it can navigate in the streets, But I think what is more interesting about it, and you can see it on the top left, how the drone stops when it sees someone, and then it continues. Now they train it with tons of data, very complex CNN, but the neat thing is that it generalizes from exterior to interior, so the drone can navigate a hallway, for example, or maybe in a parking lot. So this is pretty neat. Now, when underneath it all, you have, let's say, I think it's close to 100 images that they use to train, and this DNN is, it's a rather complex DNN. It has, 3 residual blocks that are made of convolutional layers. They have a max pool layer. They have, it's a complex network. I think it was over 80,000 neurons, just to give you an idea. This is not the state of the art. The state of the art may have 10 more times neurons, but this is a sizable network, and it provides 2 outputs, the steering angle and the probability of collision. So it tells the drone where to turn to, avoid an obstacle, and the likelihood of hitting an obstacle. And it performs really well in terms of having low error for the steering angle, having high accuracy in terms of the collision detection. And, you can imagine that we could also apply notions of coverage that our community has generated in the last few years to estimate, how well do the images cover the neurons or any other coverage metrics that you pick. My feeling is that this is completely insufficient when we're thinking about querying the DNN to drive an autonomous vehicle. And what I'm saying is that it's completely insufficient because, the network may not have been trained for all scenarios, and when it connects what it learned from 100,000 images, it may actually overlook corner cases fairly easily. So what we instead would like to do is we would like to provide guarantees that the system abides to certain properties. Now, don't get me wrong, I understand that writing a property for a neural network is not easy. It's not easy, it's not trivial, because on the first place, you're using a neural network because you couldn't maybe even specify what the program should do. It's hard to write a program that says recognize people in an image. It's really hard, or recognize obstacles in an image. It's really hard to do that. However, there are properties that we want to make sure that this system abides. For example, for the drone, I would like to make sure that the probability, if the probability of collision is low, we don't take, really sudden steering angles. If I'm taking really, really drastic steering angles, then it should only be because I'm able to hit something. Now, generating these properties themselves is hard, okay? I recognize that, and this is I think it's a pending subject for our community. But for given that property in program analysis, what we have seen in the last few years, let's say 3 years, is that there's at least 20 verifiers that have come up to verify networks. And these verifiers, given the property and the network that has been trained, it provides a judgment about whether the network meets a property. Most of these verifiers have been generated in the context of, robustness properties. But even though this verifier is supposed to provide true, false, or unknown, so property holds, it doesn't hold, or I cannot tell, in practice, what we see with DNNs is that as the DNN complexity increases, the verification time goes up to the roof, and most of the verifiers from modern networks can only say unknown. That means I couldn't even run on this network. I cannot tell you anything about it. Now, my colleague Matt Dwyer had this insight that said, look, let's consider the space of error and verifiability of these networks. And the green line represents the verifiability. The error, or accuracy bar, is in blue, and the white x-axis is the complexity. What Matt realized was that, look, there are 3 types of networks at least. There's ones that are high error and verifiable, the ones on the left side, right here. There are some networks that are low error, but they are not verifiable. Our verifiers don't scale up. The verifiers can, get up to here, and then they go up to the sky in terms of verification time. And there's some networks that have low error and are verifiable. What's the difference between them? And why why is that the case? Well, so Matt, what he thought is that there's this sweet spot in the middle that we would like to be in. And maybe there's a way to push a network like this, which has low error, but it's not verifiable, towards this sweet spot over here. And the idea is that if we can transform a network so that it is in this sweet spot, then we can provide the best of both worlds. So the solution to do this was to provide a mechanism for refactoring DNNs for verification. Now, this refactoring implies changing from a model like the top to a model like this that basically simplifies the network. And by simplification, I mean it's a loaded work. Simplification means perhaps removing layers, changing the layer type, rescaling the layer, changing the weights in the network. And the idea is that all of these will help us push the complexity of the network such that we will make it more verifiable. David has built a tool set for this that is actually quite neat, that allows us to experiment with these networks and multiple, all these verifiers that are emerging for DNNs have different features and strengths, and David has been able to normalize them so that we can more quickly build a plugin for them and incorporate them into an infrastructure that can compare them more easily. So going back to the example that I had before for DroneNet, we can see how we can simplify DroneNet from the original one by linearizing it, dropping a layer, dropping another. And in the end, what this allows us to do through this refactoring process is we're able to get something like the conceptual curves that I showed you before. So this is not quite right yet, but you can see how this is the original networks, and these are 10 properties that we actually verified or could not verify on the original network. So the y-axis is verification time, the x-axis is the number of neurons. The original network had almost 80,000 neurons, and we could not verify all the properties. That we got this basically out of memory error about 100 or 1,000 seconds, and we cannot go further. And then what happened is that we went to we went with refactoring networks and we made it simpler. So I'm going here to the left, and you can see how now we made the network simpler. So now the only thing that changed that is that instead of having out of memory, we were generating timeouts. But we reached some point that the network is actually coming down. And when we reached the 13,000 neurons, we could see that these networks actually had low verification time and at least generated SAT and unsat results. So at this point, we reached this sweet spot where the network is still accurate and verifiable. Now, the process to get there is not straightforward. So the sweet spot seems to exist, but it's challenging to find. And I think where we're going next is we're going to try to tailor this approach so that we can do verification as a function of the distance between the training and the real world. So it seems that we're trying to verify in the presence of any inputs out there. We would like to see if we can verify the system according to an input space that is closer to the training set than the full world like we're doing now. So I think I have introduced 4 techniques that cover a different space of problems and solutions. I think what I wanted to highlight here, and through the process I tried to do this in a little bit of a sneaky way, is that really I introduced the techniques to just show you the different kinds of problems that we're facing. We're trying to bring program analysis to the robotics world. And I think the distance between code and world is an ongoing issue. The system states being really complex is an issue. The constraints and the synergy between the code and the physical world that apply to each other is extremely rich. And I think this idea of trying to provide guarantees on these DNNs using perception layers is definitely still an open problem. So again, if you want to take something away, is the fact that this is a rich area with plenty of space to work on. Extremely satisfying to do this, and I would definitely encourage people that are thinking about it to either talk to me offline or about the experience I have had. I just want to say I have thought about a little bit about the roadmap to do this. I think getting collaborators is something that I'm trying to emphasize. Working with ROS or learning ROS is maybe a good first step. Get yourself an open source platform, robotics platform to play. It turns out that it's an investment that pays off in different ways, including recruiting great students. The communities where some of this work has gone is not ICSI. ICRI, ROSA CPS, these are communities where this work is also appreciated and well received, and you'll need to learn how to target them. These communities are all different. In a community like IROS, a demo is worth 100 empirical studies. And this is something that you can learn by working with your collaborators in these areas or by hitting your head against the wall. I have done it both ways. And there's clearly an investment in getting involved into, at least if you want to get your hands dirty and understand the problems yourself, it does require some investment, but very gratifying, at least in my case. So with that, let me just close by saying thanks to my collaborators. I could not have done this without them or my students, just a great bunch. And to the funding agencies, especially NSF, which has been throughout my career, my main supporter and enabler. So with that, I'm happy to take any questions.
Thank you very much, Sebastian. That was great. Very informative to get a overview of the work you've done in the past few years. Just again, a reminder for the attendees that we're writing. Please write your questions in the Q&A. So we already have a number of questions here. I'm trying to figure out what is the. I think the first question was by Danny Dig. He asked, "Hi Sebastian, thank you for an inspirational talk. Several times you mentioned collaborations with faculty from other areas. What are some of the lessons, example, challenges, and rewards that you learned from collaborating with faculty from outside of software engineering?"
Yeah, thank you, Danny. That's a good question. I think that the lesson, I think there's there's this notion of delay gratification, I think, that I have experienced working with faculty in other areas, in the sense that, it does require an investment up front to just even have a common vocabulary, understand each other. What do they mean when they say, a model, or in my case, what is a state? When they think about state and we think about state, we're referring to very different things. So just identifying the common vocabulary was challenging. And I show you the good collaborators that I have had, that I have, worked through several papers and proposals and things like that. There are many of those collaborations that were much more ephemeris, that just didn't go anywhere. So you got to be willing to make those type of investment, take those type of risks. But I have learned so much more by working with people that are further away from my community. In a sense that, I feel like in robotics, it felt like I was getting a new PhD or a new master's in some way, right? I was not aware of the world that resided outside software engineering, except for, I was familiar with it, but I did not understand it to the level that I do now, and I couldn't do it. I could not have done it without those collaborators. So definitely, they accelerate your learning. They enable you, and I think the tricky part is that you need to be willing to make the investment.
Thank you. There is a question by Debbie Katz. The question is, do you have a citation for a paper on your work that addresses the problems and solutions in inferring and monitoring physical invariants? I may have missed the citation, and I see that there is an answer in the Q&A.
Yes, and
I don't know if you want to add. Go ahead.
Yeah, that answer seems to be the right one, Debbie. So I think what I would add, though, is that the two pieces of work that we have on that, and the third one that is coming, have appeared in robotics venues. So in a sense, they the robotics community has been very excited to see how we adapt the advances that we have made in program analysis and software engineering to their domain, and their feedback has been extremely encouraging. So so this is one case where we felt like, you know, that you feel a little bit like a trader because this is work on invariants and program analysis and stuff like that, but it was the right venue for it.
Thank you. Another question by Danny D. Sebastian, all right, I lost that. Sebastian, I like your example with refactoring for improving the verification of DNNs. Where else do you see refactoring being applied to DNNs?
Yeah, you know, so interestingly enough, we stumble upon the idea of refactoring here. We're starting with the idea of re-architecting DNNs at the beginning. That means just changing the layer types and this and that. But then it felt like refactoring was just much more appropriate, because we thought about other things that we wanted to do that went beyond just changing the architecture. We were thinking about changing the weights and maybe steering those values towards certain directions to help a verifier do better. In terms of what else I see it, it seems like I would think though that there is a lot of refactoring. There are different names going on already in terms of how the data that goes into the CNN, so that comes out of the CNN, is wrangled for different purposes. But you know, I do wonder whether, and I think I'm barely familiar with some work, for example, on changing the DNN structure to actually, you know, there's this concept of distillation that we use, for example, in our refactoring approach. That distillation is actually the idea that you can distill a simpler student network out of a teacher network. And that feels like refactoring to me. And the idea of that is you refactor to fit your network into a smaller device with a smaller memory footprint or something along those lines. So, so my guess is that although the refactoring name is not being used, there's definitely cases where that's what is happening. It would be an interesting take on that, Danny, given your background about, you know, whether there could be an enumeration of the instances where really refactoring is being used to change a DNN for different purposes, or the data that it uses.
Sebastian, I actually have a follow-up question to that. So when you talk about verifying the, I guess you mentioned simplified DNNs, how do you provide assurances that the verified properties in the simplified DNN actually hold in the more complex DNN? I probably missed that part in the talk.
Yeah, so it's a very good question. So what we're saying is, look, you know, if you give me a property, let's start from the baseline. The baseline is that these big DNNs, we cannot even verify them. We cannot say anything about them. I don't know if the property holds or doesn't hold or anything like that. So if I distill it and I tell you it doesn't hold, you're already ahead in the game. At least you know that it doesn't meet the property. Mm-hmm. But I think what we're arguing though is that we wanna guarantee that given a property, if it held on the big network, we wanna make sure it holds on the smaller ones, and we wanna make sure that more of those properties hold on the smaller network.
Okay.
So it's basically, you know, if you give me 10 properties in the large network, only 3 hold, and in the smaller network, we can get you at least more than 3 properties. And the accuracy, I mean, this is the cost. The accuracy is going to be lower. So that's a trade-off here. Mm-hmm. We're telling you, we're going to give you a verifiable network at 2% loss in accuracy. Is that acceptable? In some cases, it may not be. So the trade-off here is, so there's no freebie here. There's a cost associated with that gain in verifiability. What we're hoping is that the sweet spot is broad enough that that we can reach a very good compromise.
I see. Okay, interesting. All right, we have one more question from Afsoon. The question is, or the comment slash question is, thank you for the great talk. Given that many of the techniques you talked about rely on knowledge about the physical world and the connection of the code to those, how much input do these methods require from experts, and how much automation do you anticipate in the future?
Yeah, thank you, Abson. That's an excellent question. So the short answer is that a lot of the infrastructure we're building. So let me start one by one. So in the first case of dimensional analysis, we don't require anything. Everything is automated. So the analysis actually are built on top of these inference that allows you to get the physical types directly from the analysis, either by inheriting from a class from which we know the types, or by how you name variables, or how you pass information around the code through the data flow of the code. In the case of text generation, or in the case of invariants, we developed a library with physical invariants in mind. So we were the experts that developed the library. The neat thing is that both of these approaches, you need to do this once, and then you can reuse this over a big, large number of systems. So there isn't a cost in building these tools, but then the propagation of the benefit is much broader. For the one that I talked about, text generation, you do require a physical model of the robot. And that one, you're right, that one will require an expert to give you a model. The good thing is that when you talk about robots, you will be hard pressed not to find a robot or to find a robot that doesn't have some physical model or some physical model that you can adapt to that robot. So for example, for drones, most drones will use the same physical model. Most quad rotors will have the same physical model. Even when you go from a quad rotor to an 8-rotor, you may actually grab some form of that model and adapt it. Ground vehicles, if they have 4 wheels, the models are very, very similar. If they have 2 wheels, they're going to be slightly different. But my point is that, yes, you needed some expert to tell you what model to use as input, but those are kind of the bread and butter. They're not going to break the bank by providing those. Even simpler models would help us. And I think that's probably a takeaway, is that just a little bit of the physical world that is included here could have tremendous benefits.
Thank you. So for the attendees, feel free to leave your questions in the Q&A. I have I'm offering to buy you your favorite beverage at the next ICSI if you ask a question. And if it's anonymous, then I'll have to buy a beverage for everybody that is in the attendee list here. So we have one more question from Danny Dig. He says, I appreciate you doing pioneering work at the frontier between the 2 disciplines, robotics and software engineering. When you publish in robotics venues, did you run into situations where they reject your papers on the basis that it is not a perfect fit? Do they send you to the software engineering community instead? Conversely, if you try to publish this in software engineering venues, did they tell you that it is a better fit in the robotics literature?
Yeah, I mean, we have experienced both. You know, I don't want to say I have learned how to deal with such rejections. But you learn how to tailor the work to each over time. I can sympathize with people who are working across communities, because I think this is a common situation that you would face. The good side of this, though, is that I think that if you pay attention, after a while, you learn how to talk to a community. And again, I think having a colleague that sits there might help to target the community. But you need to go through those situations where you need to tailor the work to fit that community, and you may still be sending back. You know, we have had robotics papers that said, look, there's too much code analysis here. It doesn't seem right for our audience. So you learn how to emphasize the work for the right community. Still, I mean, we get rejections of the kinds that you get, but part of it is putting your foot in the community and saying, you know, for example, Iris now has a software engineering or programming and tools track that wasn't there 5 years ago. So I think that there's also this neat opportunity of setting a trend or opening the community to other type of papers that they were not used to seeing. I'm hoping we can do the same thing at ICSI. You know, there were clearly several papers on or DNNs or things like that in the last couple of years. I don't see many papers on robotics, and these are the systems that are, I don't know, that should open your eyes more than anything. The things that these type of systems are able to do and the complexity that is inherent in their development. This is where I hope our community has a track like this, you know, in a few years from now.
Thank you. There's a comment by Danny Dick. Thanks, Sam, for your offer. You owe me 3 beers so far in Madrid. So the offer wasn't that I'm going to buy you a beer for every question. It was, if you ask your question, I buy you 1 beer. If there are any other questions, please put them on the Q&A. I have a question, Sebastian. So in your type inference work with ROS operating system, you talked about how you guys, I think, manually pretty much went and tagged the various library APIs to figure out the dimensionality of the data and so on. Do you think, so of course, robotics are one type of systems, but I mean, they're not the only type of cyber physical systems, right? Where these issues come up. What are your thoughts about, I don't know, can we do the same thing, for example, with Android-based systems or other kinds of operating systems that are being deployed in these sorts of cyber physical systems?
Yeah, that's a very good point. You know, I think the general approach of providing this mapping, I think, would be applicable to those systems. And I'm thinking not just robotics, right? I mean, if you were thinking about a system that does weather prediction, right? There's a lot of units involved there, a lot of dimensions involved there, and clearly having dimensional, you know, consistency would be helpful.
Mm-hmm.
So I think what I would take out of that though is, you know, we have built a domain-specific type system, and I think that's something that is translatable to many domains. I think what is probably unique about it is how we have been able to generalize it to this very de facto robotics domain through just 2 automatic inference mechanisms. So all these type systems that we talked about could have done by, you know, Sam, you and I could go in and actually label every variable in the code with an appropriate unit. Mm-hmm. Very expensive and actually very fault prone. So John Paul did a study where he found that almost 50% of the annotations that people make on units are wrong. Mm-hmm. Mm-hmm. So it's slow, it's expensive, it's fault prone. So the key contribution here is our ability to infer the types and provide and lower the cost so that this analysis can be done without having the developer put in the type of each variable, but really inferring it. So in the domains that you're talking about, extending from ROS to, you know, other robotics libraries or other domains completely, I think the key piece here is how do we extend it so that people can infer it quickly, infer it at low cost. Mm-hmm. And I think the other piece that is interesting about robotics and may not be another system is this idea that dimensions is just the surface, right? And the code is so disconnected from the physical world in which it operates, just like in cyber physical systems, that we need to provide these interpretations for the code. You need to be able to interpret the code and say, this is how I interpret this variable or this concept in the physical world. Mm-hmm. That decoupling is just, we have abstracted too much about things that we need in this type of code.
Mm-hmm. So it seems like the biggest bang for your buck is going to come if the people that are developing ROS actually put in the information as to what kind of type data is coming from the library, right? I mean, that way, everybody that is building applications on top of it would get that for free, basically.
Yeah. And these libraries do not change often, actually. These libraries are not going to change often because there's a lot of code relying on them.
I see.
So we haven't pushed for ROS to incorporate these as much. I think right now we are trying to see whether we can go much beyond, to go much further than dimensions. Like I mentioned, you know, physical properties. You know, can you add a vector with a point? Is that even legal? Can you add 2 vectors? I mean, what type of operations can we apply that are legal in the physical world. And I think that's where the big payoff is going to come from.
Mm-hmm. Thank you. There is one more question. So Miriam Kim is asking, Sebastian, I have a question about your work on refactoring DNN for verification. Is there any relationship to model compression of neural network? A general question related to this is that, do you see another community such as robotics doing work with similar to software engineering researchers, but may call the type of work in a different way?
All right, so I thought there were, let me just read it some, because I thought there were a couple of questions
there are two questions in there, yes.
Yeah, okay, got you. Yes, so there is a relation to compression, although the mechanism so compression could be actually considered another form of refactoring, Miriam. So absolutely, there are different transformations, I guess, that we could apply to make the network simpler for the verifier, and compression is another one that we're looking at, absolutely. And I think there was a general question.
I can repeat that. A general question related to this is that, do you see another community such as robotics doing work similar to software engineering researchers, but may call the type of work in a different way?
I mean, vocabulary in general is a difference. So I think I have seen cases of these. I mean, you see cases, for example, where I mean, verifications of DNN is a big topic throughout the CPS community, and CAV and many other communities that are, well, I guess CAV is more like us, but if you think about CPS, they're very different. But even then, I think you do have some overlap, and I think that's why it's important to have a foot in those communities to understand whether they're doing something similar or not. In the case of particular CPS, for example, I have seen analysis and verification approaches for such a systems. I think one difference there would be that the focus is primarily on the model, and they pay more. I think they are kind of the opposite of us. You know, they put more emphasis on the physical model and less on the cyber model, and we are all cyber, we're all code. So in the context of robotics, I have seen, you know, the example that we had on the about the invariance of the drone landing on the moving platform. I have seen a couple of papers after hours that is something similar to that, using different mechanisms where they apply invariance directly to the sensors instead of to the messages between the processes. So I can definitely see, you know, some overlap, like you mentioned. There are clearly differences, and I think our focus on the program and the code is something unique and something that we have to, that we can definitely add values to these communities.
Mm-hmm. So Miriam Kim posts another clarification. She's saying, maybe a better way of asking my second question is that, do you see a lot of interest / overlap from robotics researchers on doing testing / debugging type of work, and that the focus on ensuring correctness is not primary concern for robotics researchers?
Oh, okay, I got you. I misinterpreted the question. So I think there's you need to find the right audience within the robotics community. I think a big chunk of the robotics community is interested in getting the next exciting prototype of an idea out there, a robot that does something X that is super exciting and novel. So I think something that we identify as being useful in our work is trying to motivate the work in scenarios that they could relate to understand why testing or debugging or verification was of value to them. I think that the other thing that we're finding, though, is that the tide is changing on this. It was very different in 2012 that I recall how people thought. For example, colleagues thought that you know, the code is always right. I mean, there was a very naive attitude about the systems and how the complexity was primarily on the hardware. I think as these systems are being used more and they become an integral part, I think this is changing. But this is, again, this is my feeling about it based on the reactions that we're getting from work submitted to these venues. But I think I see the tide changing.
Let me see. Okay, one more question. from Joshua Garcia. Hi, Sebastian. Thank you for the great talk. I'd like to hear more about your thoughts on creating a domain-specific type system for autonomous vehicles, i.e. self-driving cars. Could you please elaborate?
Yeah, so if you think about a domain-specific type system that we created was just for ROS, and if you have an autonomous system built on ROS, so early versions, for example, of an open source AV was built on ROS 1.0, and I think they're still on ROS, and this particular vehicle uses ROS library, so you could apply our system directly, but this is the general version of the type system. If you're thinking about a self-driving car, besides velocity, acceleration, jerk, force, and all those dimensions, if you think about particular attributes that would be relative to that domain, then you can extend the system for the autonomous domain, right? So the properties that I'm talking about, the types that I'm talking about right now are type of physical worlds. The idea that we had was to have something general that applies to all robots out there, all mobile robots, including AVs. But if you want to concentrate on AVs, I'm pretty sure that you can come up with certain types that are particularly applicable to them, right? I mean, notions of friction or the effects of elements that interact with the road. Those are very particular types that are only useful to AVs, and there are libraries that deal just with those types that would have to be typed to detect the errors that we found. I'm happy to talk to offline, Josh, about this. I have some ideas about AV types in particular, but I guess in terms of the talk, what I was referring to is providing this general support so that any time that you have a system that interacts with the physical world, it represents or it respects the semantics of the physical world in which it should operate. I think that's what we're trying to get at.
Thank you. There is one more question by Danny Dig. Oh man, Danny Dig is gonna get really drunk at the next XC. I'm gonna have to buy him a lot of drinks. He's asking, when you work with robotics code, did you notice how it is different from the code developed for business / enterprise systems? For example, you already mentioned that robotics libraries change less than other libraries in our field. And have you observed other differences?
Yeah, so there are a few things. I mean, let me answer this at two levels. I think in the context of ROS, what I noticed is that the core libraries may evolve less, but the ecosystem of ROS is evolving all the time. Everybody that creates a new sensor is going to create a ROS node so that you can read data from that. So that the cool thing about this system is that I can grab a component like a lidar, replace it with a new lidar, replace it with its process-to-process lidar data, and the rest of the system stays the same. So this idea of reusing, they got it down in ROS with this concept of these processes that communicate through standard messages. So that level of change happens all the time. But just in particular with your question, I think what you can see in the code though is that many of the folks programming these systems have different training that we do. So it's a broad robotics community. So they're not trained necessarily as software engineering. Maybe of them have a training in electrical engineering, mechanical engineering. So the code may look very different than the structure of the code, the thought process to organize it in classes or things like that look very different from what you and I would do. So I think you'll find a range of software engineering experience in the code that gets out there, and some of it is used by tons of people. So that's the part that makes you think that maybe the code has not been it's not up to the latest SE sniff test, but it is being used extensively. So code structures are going to be surprising. So one particular example that comes to mind is how everyone turned to, I mean, there are many techniques that we think about would be great for these systems that when you run them, they struggle. For example, much of the code may not have any branches. Many of the codes, like a controller, it just consists of, you know, a complex series of equations, but that has barely any branching. So if you try to apply a technique like, let's say, symbolic execution to test a system that builds on the idea that the code branches at every so many points, and you find that there's no branches in this code, just a branch or two, then techniques that we thought would be very successful just struggle to actually explore the input space effectively, because the complexity doesn't come from the branching structure, but it comes from the data that is embedded in those equations. So very different flavor in that way, in terms of the differences in the code. I think I diverge a little bit from Danny's original question, but definitely I encourage you to check some of these open source projects that have tons of code available to get a sense of, to get your sense to see where you see the differences.
Well, I think we're at the end of the session almost. Actually, see one more question. Let's see if we can get through this one. Okay, so last question. Shiva Najati is asking, what is your opinion about the keynote by Nancy that we should not look for safety issues at the code level, in parentheses software, but instead we should study CPS/robotic systems at the system level?
Is it okay to admit that I only listened to part of her keynote?
This is being recorded, just remember that.
It's just for us, right? So look, I see what is, in an ideal world, I think you would just look at the requirements or maybe some model of a system. In practice, these systems are, you know, and this is something that, for example, the CPS community tends to do, just look at a model of the system and they analyze the model with the sprinkles of code throughout. I think what happens is that many of these systems do not evolve in the waterfall way that you would expect, where you have the requirements and the safety, you know, the safety case made up front and the design and the code. A lot of these systems, there are tens of thousands of robots out there that do not follow this model, that are really driven by very sophisticated code bases that do not follow that pattern. And the question is, do we try to fight this tide and say, look, you need to follow this particular methodology? I think we have seen many cases where our community has struggled to do that, to put it nicely. I think my approach has been always to see where the community is at, how can I help it right now, and how can I help it at the same time guide it towards something that is useful, but not just ask them or tell them this is how you should do things, because you know, because it feels really like it's hard to have an impact when you operate that way. You know, I think that if you build today a tool that can support the ROS developers, the tens of thousands that are there, the millions and millions of lines of code out there, you could have a major impact in making the systems that are there safer. And that's the way I decided to proceed about it. Recognizing the merits of going by some safe cases and things like that. And I think there is a space for that. I think there's a space for, you know, high-end avionics that are able to do that, or some medical equipment, but there are many other systems that are not going to be able, or they're not going to be inclined to do that.
Thank you, Sebastian. I'd like to thank you again for engaging talk. I'm glad you came in, you gave this talk. It exposes the ICSI community to these challenges that are very much software engineering-ish in the robotics world. I think this was very, very informative. And I also like to thank the attendees for asking a lot of questions. And I hope to see you in the future technical briefings. So we have one later today. And so this pretty much concludes today's technical briefing. Thank you.
Thank you, Sam. Thank you, Jay. Thank you all. Bye-bye.
Bye.